Welcome back, everyone, after this well-deserved break. We are now entering the last part of our conference, and now we will talk about sustainability things and more about centering and self-healing concepts that are part of our roadmap. And I start directly by inviting Marcel Vey from KIT to talk about Lifecycle sustainability analysis of present and future battery systems. The perspective we always have to have in mind when working and doing research in this field. So welcome, Marcel.
Thank you very much. I will share now my presentation. Hopefully it works.
And could you also share your face so we see you?
The bandwidth, we have some issue with the bandwidth of the connection, therefore we decided not to share the camera. Okay, I hope the first slide is online.
Yes.
You're not in presentation mode yet, but if you switch to presentation mode, then that would be great. Currently we see your power. Now we have seen the presentation, slide number 1.
Yeah, but it should be in the presentation mode.
Yes, it is. Can we just go ahead?
Right now you can start. No.
Okay. Good. So, welcome to my presentation regarding life cycle sustainability assessment of present and future battery systems. And we can truly say that present lithium-ion batteries are unsustainable. In respect, they use critical raw materials, as you know, like cobalt, lithium, nickel, copper, but also others. The production costs and life cycle costs are quite high and still too high in comparison to other technologies. The environmental and social impacts of the production are really high. The technical performance needs improvement, and that means not only energy density and power density, but also cycle lifetime, or for instance, internal resistance is quite important for the use phase. And of life, the recycling is still too complex so far, and there needs tremendous effort to reduce the efforts which are necessary for the recycling. And last but not least, there are of course also safety issues during production use phase, but also the second use and recycling phase, and that is strongly influence also societal acceptance. So that means present battery systems are not really sustainable, and the task is that the future battery system, the post-lithium system, they should have much better sustainability, or at least increased sustainability performance. And you see here the different topics which you have to address, and that's really from raw materials, from the design of the batteries, the production or the manufacturing, the use phase, then the second or third use phase, a highly hyped topic in the moment for lithium-ion batteries, and last but not least also the recycling issue. You can assess the sustainability with a whole bunch of methodologies. There, for instance, it's MFA, material flow analysis, which you can use especially for resource issues or recycling issues. Then the whole family of life cycle assessment or life cycle sustainability assessment. And today I will especially show results regarding life cycle assessment, LCA, or life cycle costing, LCC. In addition, there's also the methodology multi-criteria decision analysis, MCDA. You have to use that if you have to combine the different dimension of sustainability, maybe like social issues, environmental issues, and cost issues, and to find maybe the most promising option of a technology. You could also use a sustainability concept. It's relatively complex, a lot of indicators, and it's really time consuming, but also a few people trying to use that in the development phase of new materials. Also social analysis, the acceptance, for instance, of technologies are quite important to address in the end, because finally the society has to accept this new technology in all the different aspects. And then TA stands for technology assessment, and that is more than a social dimension or political dimension, which you can also address sustainability of new technologies. Well, I will just highlight actually a few parts of these different perspectives, and I skipped the raw materials part, but of course you're aware that there are issues regarding, for instance, cobalt and lithium. And if you are interested in that, please visit our homepage and find several publications regarding the use of critical raw materials. And even in the session before from Simon Clark, there was some presentation from our results in Nature Reviews. And I will now focus on the design phase and the prototype phase, and that's closely related of the Big Mac, of course, of the battery 2030 plus. And here we would say that in this early design phase, it's quite important to use prospective LCA, life cycle assessment. Because in this early design phase, you're really determining the future environmental impacts if you then have a cell or battery system. The problem is that we have this time the so-called Cambridge dilemma, and that means we have restricted data availability, and that is a big issue. On the other side, in not doing that, then maybe in the end you have at later stage problems to repeat your development, because now you have maybe not to use a certain element like the most critical resources, whatever. So from our perspective then, prospective LCA supports the development process and identify hotspots, and that can be used, this information, to improve the system for the next development step. Then we could define together with the technology developers then really development goals, also in a certain perspective of a future application field. And then also in the design phase LCA, this perspective also can be used for screening. I cannot go in all the details, just maybe to highlight that, well, we will focus our work, or the focus should obvious, the work should be also focused on the present technology, but also the future technology, which is here addressed in this nice graph from my colleague Dominic Presser. And so that means, therefore, regarding our work in the past, that's just a few selection. We started actually first to understand what are the biggest issue of present LCAs of existing lithium-ion batteries, because the present LCAs are, from our perspective, not so much robust. So, but that's of course important that we can get a new system with the present system. Then we did a lot of LCAs for emerging system, and we produce the first available LCA for sodium batteries, for saltwater batteries, or for instance for magnesium batteries. But we also used this kind of approach for the support of screening of materials, which also, of course, is quite an important step within the development phase. Production means more in this as a next step, more the manufacturing step, and we do that for post-lithium battery cells. And we investigate in Karlsruhe here only on laboratory or on pilot scale the different production steps and estimate then the material and energy efforts which are necessary to produce the cells, and think about what would be then the effect if we upscale the production, for instance, from 8 cells per day to 400 cells per day, and then maybe further to more industrial scale. And then with this kind of knowledge, of course, to improve the overall efficiency of the production. Then the use phase, also regarding scenarios, here in the next slide, you see there we did an LCA investigation regarding the CO2 footprint, and you see 4 different stationary application fields and a comparison of present existing battery technology like LFP, the first, then maybe the second last is the lead acid batteries, and the last one is the vanadium redox flow battery. So we compare different batteries regarding a certain application field and looked for the CO2 impact of this technology. And we cannot go in detail of it, but at least I would like to show that there are really huge differences between the technologies and also depending on the requirements of the application fields. And we did that also for cost analysis, and so at least we really see the increased understanding what are the effects if I change also some parameters within in my system, like for instance the cycle lifetime or the energy density. And of course, with this basic understanding, there could be also could be then used for other purpose to compare with future systems. And that you can follow up here in this publication. Then last but not least, we jumped over the second use phase, then recycling and refurbishment. And that's, of course, quite linked to design, because design determines, of course, also the future option of recycling. And that was also a big issue within the roadmap of Battery 2030 Plus. And here, if you see the effects of the cycling of batteries, then you can see sometimes you have a positive effect. If you recycle the batteries, that's in green, but sometimes even red. But even the green parts are really optimistic assumptions. So we really have to focus on the recycling issue, because the efforts for the recycling at present are still too high. In this case, actually, we try to compare totally different technologies. That's a saltwater battery, the first vanadium battery, and the lithium-ion battery for a certain application, and just understand what are the effects of recycling regarding this application field. And you see here already now the results regarding a resource impact indicator, and you compare the first is the lithium-ion batteries, the second is the saltwater batteries, and the third column is the vanadium redox flow battery. You see here, if you regarding the resource impact indicators, these two ones, that the lithium-ion battery performs best without recycling. If we consider recycling, that's the next row, then the situation is changed, because if I consider then also the recycling all over the whole life cycle, then in this case, regarding the resource indicator, the vanadium redox flow battery performs best. So recycling is quite important from a methodology point of view, but also regarding the technology development. So, and from our perspective, the biggest challenge in the future is the recycling value of materials, because today we have already now an recycling, which is really energy or chemical intensive, and you can only finance this recycling if you have really high material value in it, like for instance cobalt. But now the situation is now also with the trend towards from NMC 111 to NMC 811, there's already a loss of the value, because the cobalt is replaced by nickel. And with LFP, there's already no cobalt in it, or in the future system, some totally other materials are in it with a low material value. That is the biggest challenge for the future. From our perspective, therefore, there should be, for the future system, mechanical treatment, an option that allows direct recycling of the materials and within the cell. And only in this case, we can really ensure the sustainable development in the moment. And that's actually also maybe with this graph from the Afghan National Institute, we say, well, it's really important to increase the interdisciplinary work between recycling as experts, maybe sustainability experts and technology developers, and to include methods like design for recycling or even design for sustainability already in the early phase of technology development. So that's actually my presentation, and at least I hope I could show you some interesting points how you could consider also in the future the sustainability issues already in the development phase of your considered system. Thanks a lot.
Thank you a lot, Marcel. Very important topic and a little bit challenge. I think we are a little bit challenged by your view and your results, and I think that's really important when we compare things like you do. I open for questions, see if we can have something coming up in the chat or in the question and answer section. You said in the beginning of your presentation that you were not really happy with this the current LCA methodology. Can you explain a little bit more what you find is the problem? Is that the basic sort of data that we need to sort of support with, or is the way you put it together? What do you say, Marcel?
Yeah. Okay, there are actually several issues, but one important issue is that many LCA only refer to only a few primary data from really existing measurements. That means a lot of LCA based on data from others, and therefore there's not really a robust assessment. And if there is a wrong data in the community, then everybody use this wrong data and cite it again and again. And so therefore the LCAs at present are not really robust. And there was a lot of ongoing discussions regarding some recent publications, how robust results are, or why the results differ from publication to publication by factor of 2. Some such things happens and should not happen. And that means there's a high necessity to have primary data in real cooperation with people which doing the production of cells. Only with that, with this primary data, we have more robust analysis, and then we can compare with future and present systems.
Thank you. Now I can see a question. One important question coming back is, how about Second Life? How would that affect your assessment?
Well, Second Life is present in EU, also maybe worldwide, and big issue. The idea behind it, of course, that the battery is not used once and then recycled, so that you reuse it for another application. Most common, the idea is to use batteries from the automotive system, then later on in a stationary application. And if this happens, then of course you can allocate the environmental impact to the first and second use. And then in this case, then you reduce the overall impact and split it to use phases. And so of course it's much more environmental friendly in comparison to others. But the second use and third use is still a big challenge, and there are still some open questions. So it's a nice idea, and a lot of people use it, or also advertise it to use it. But we have to solve it. And from an environmental point of view, it's quite important, to extend the lifetime of the battery.
Thank you very much. I think we need to move on, but you have one interesting question in the question and answer about direct recycling versus hydro. Thermal and pyro processing. So you can maybe answer it yourself, because we need.
Okay.
So thank you. Great presentation. I now welcome Jean-Marie Terrascon from Collège de France to discuss his topic, which is conceptual membranes enabling sensing and self-healing for upcoming battery applications. So please, Jean-Marie, and you're welcome to show your face. I hope your bandwidth is good.
Is it okay? No.
We hear you, but we see your presentation.
Okay. So good morning, everyone. And I would like to thank, of course, Christina and Mark for organizing this forum on the European perspective on batteries of the future. And what I would like to do here is just to give you a flavor of the type of research that we are doing within the spirit of Battery 2030. We are going to see the risky research is TRL 0, but you will see more or less what we are shooting for. So first, why should we bother about self-healing? You know that in the battery, you have the electrodes and you have the separator. But you have several issues that are related to dry growth, to redox shuttles, and we'll see especially this point, polysulfide and so on. You have the SEI, and also you may have the cracking of electrodes. So the question is now, how can you cure all these issues? We can do it by using at the electrode level self-healing polymer, supramolecular bonding. Now we'll come back on this point. We can also use kind of nacelles. We can put it both in the separator and the electrodes. And you can work really at the membrane, as a functionalization of the membrane to make it more smart and so on. So today, what I would like really to focus is on the membrane and how to introduce self-healing functionality. If you look at the membrane of batteries, you need to realize that this is more or less the way that the membranes that you have in your body are working. In this body, you have this lipid bilayer in which you have different types of molecules, and one that is very important is this kind of protein channels, as you can see here. And these protein channels are really living, they are traveling, and they can either close or open, and this produce bioelectric signals that, as a matter of fact, are triggering your brain and so on. So the question is now, can we use the biologic membrane and can we implement it to the field of battery? Because when you look at all this membrane, most of the components, at least the integrity or the structure, I will say, is really governed by supramolecular interaction. So the question, can we do the same thing for battery? Can we use supramolecular chemistry and try to find some molecular recognition, some high selectivity, some adaptation, reversibility, and have some kind of matrix that I will respond constantly to local changing environment. And I should say that this has already been done in the case by designing some self-healing polymeric membrane relying on the principle of dynamic coordinating based on supramolecular host-gas interaction, and there is a group of compounds who have developed this for silicon electrodes. But this is more or less just simple self-healing. So what we want to do here is we want really to go one step further and to design a smarter membrane. So here you have 3 points that you need to address. First, we want to have a species, we want to trap them, we want to release them on demand, and of course, we want also to be selective. So this is more or less a type of mission and objective that I'm going to share with you now in this presentation. So to do so, first we are going to define a supramolecular material, and in this case, there is nothing revolutionary. We are using cyclodestrine that is well known. These are this kind of, I will say, panel-shaped molecules with protein function. And here, we are going to see more or less how can you make some host-gas interaction with really some kind of species that you have in the battery. And for proof of concept today, we are going to pick up this kind of polysulfide, where we know, as clearly indicated picture, when you put cyclodestrine with polysulfide, you have a decoloration, which means that in this case, you have some kind of trapping. So we are going to look at this kind of host-gas interaction, and to do so, we are going to do it by NMR. And by NMR, what you are going to look, if you look at the spectra at the bottom, which is a pure cyclodestrine, and now, if you go in the case where you have put some kind of polysulfide species, in this case, sodium-2 S5, you can see that you have some kind of signals, namely the protons H3, H4, and H6, which are inside the cavity that are totally shifted. So this is a clear indication that the polysulfides are not going around cyclodestrine, but inside. So then we need really to understand more this type of interaction, and we look if we can define and compare what will happen depending on the type of cyclodextrin, which are alpha, beta, and gamma. As I mentioned to you before, they depend on the size and so on. And what we are looking at, we are measuring the y-axis, the chemical shift, as a function of the concentration of this X5 minus polysulfide. And we found that the association constant is the greatest by and large for beta cyclodextrin, which is at the middle, which means that this is the cyclodextrin which has the most affinity for this polysulfide ester. So having this, we use now this beta cyclodextrin, and now we try to see if we have a different type of selectivity between the different polysulfides. And this is more or less a curve that I represent here, and you can see that you have indeed influence as the, of course, the S5 is the most sensitive, while the S4 and the S3 minus has less activity with respect to cyclodextrin. So this is more or less a steric effect. So having this, we can go one step further, and one thing that is great about cyclodextrin, which means that you can track this kind of species, and then what we found, that a function of temperature, you can really release this type of species. So which clearly indicates the first indication that indeed, in this case, we can do non-autonomic self-healing using temperature as a stimulus. And you see very well how this stuff will work. You have a membrane in which you will pick up what the polysulfide species, and then you want to release. You just need to change temperature, and you will release the species. And of course, you need to orient which side of the positive or negative you will release. So this is more or less the first part in which I show you more or less how to design the kind of non-autonomous self-healing membrane. The second part, now I want to move on, is addressing the issue of selectivity. How we can know which of these polysulfides is going to the membrane. And here, I am going to use the classical technique, nanopore sensitive technique. As you can see here, it's very simple. You have a simple electrochemical cell with two electrodes. You are going to apply a bias voltage, and you can see that you have a small hole in the middle. And what is happening here, every time that you are going to have a molecule that is going to go through this small hole, it will block the current. Then why you have the current response, where you can see this kind of dip, where in this case indicates that you have really a molecule going. So this is certainly new for you guys in the field of batteries, but it's not new in the field of biochemistry, where they are using this kind of technique with this kind of electric detection to do the sequencing of amino acids or conformational or ADN. So now, when you look at the signal, you can have, of course, the dwelling time, means the time that the molecule will stay in the hole, and you can also have what we call the current blockade. This is this current blockade that we are going to use there. It's going to be very important because it's going to do the discrimination of the different polysulfide species. So how we do this experiment? A little crazy, certainly, but you are going to see. We take, in this case, a lipid bilayer membrane, as indicated here, and we are going to inject, in this case, a protein. Remember, the same gate, protein gate that I showed you before, the human membrane, where it's going to have a defined size. And then here, we are going to use the interaction between this protein, hemolysin, and cyclodextrin, which cyclodextrin is going to be used as an adapter to really screen the various polysulfide species. So the experiment is as follows. It's conducted in water with a condition indicated here, and you can here nicely see what will happen. And of course, when you polarize, what is going to happen? You are going to create electric osmotic flux, which is going to drag the cyclodextrin to this kind of open cavity of where we can outside. So the way that we do this, if we have a water solution, we can operate in a normal environment, where you can see, of course, the current, as we have mentioned before, are very small. We are talking about 3 currents, so you need to have a Faraday cage in order to get out all the noise. And here you are really looking at the practice. And what you observe, I'm just showing here 2 events. You can see when you have only cyclodextrin and blue, you have the signal, you have a current blockade. And then now, you have a cyclodextrin that has complex, where you have both gas interaction with S5 2-, and in this case, you obtain, of course, a large blockade signal, which means that you have detected the species. So these are two single events. In order to do the measurement, you need to do statistics, and you need to look more or less a function of time, how many times the molecules are going to go through or to bounce on this pole. And you have, in this case, where you have the cyclodextrin in blue, and then you mix cyclodextrin with the polysulfide, and you can see the different signals. From this, you can obtain general distribution, which is a graph with the gray, which is in the bottom, and then you can do deconvolution, in which you can nicely see more or less the separation between the pure cyclodextrin and the one that has made a complex with S5 2-. So this, of course, you can extend now to other type of polysulfide. This is what we have done it, where now you can see all the different polysulfide. And you can see, you look at the current blockade, the white axis, you can see that we have different current blockade, which means that in this case, we can discriminate all these polysulfide species. And at the bottom, I am putting the current blockade as function of number of filters, and where we can definitively determine or select it. I should say, this is only the first time the possibility to discriminate in aqueous media different polysulfide with a single sulfur atom resolution. And this enables to sequence species to memory. So this is great. And then after, of course, if you are scientists, we can dream toward Mars organic membrane. You can envision battery of the future, like you said, where in this case, you will have the biologic membrane with this kind of protein channel that are going to govern and to let ions to go to it or not, depending on you want. And then you can as well use temperature to do that. Now you need to dream, but in science also you need to fit into the ground. And what I show you so far, all what we have done is done in aqueous electrode. And of course, if you want to go to lithium filter battery, you need to move to organic electrode. And here, we need to be honest, the task is going to be complicated. Why? Because everyone knows biologic membrane love water, they hate organic media. So which means that we need really, in this case, to change and to move really to this kind of nanopore polycell membrane. So using this, what we are expecting to do is to use this nanopore membrane, which is silicon nitride, in which we can do a microwave lithography with this kind of nanorods, and we can really select the different species. We can also do cyclodextrin, as indicated here, with solution. And we can also, in this case, take a solid-state membrane and go to blast into it this kind of cyclodextrin, where in this case, we are going to take advantage of the temperature. But of course, if you want to do more familiar with the battery, an obvious problem that you want to target is try to really be selective to reduction of species that you have in today's lithium-ion batteries, which means alkyl carbonate, how you can prevent them to go to poison the positive electron. You need to do this kind of sequence. So this is more or less all this question, hopefully, is that to provide a feedback to all these questions regarding passive and active protein batteries. So this is more or less what I want to share with you, guys, about the spirit of 2030, where we are conducting research, which I should recognize is TRL 0. Thank you for your attention.
Thank you. Very exciting perspective, I would say, on quite complex chemistry and also involving biology. We have here one question from Susan Sananes. How these temperature changes can affect the cell performances? Can we imagine that with a high current pulse, we can reach reversibility in the cyclodextrin polysulfide complex?
Okay. So, yes, and this is an interesting question where people say you need to go to high temperature to switch the capturing and the release of the species could be a problem too. But if you follow the literature nowadays, you found that a lot of systems, in order to do fast charging, people now are heating the batteries to 40 to 60 degrees. And there is some recent paper in June, mainly, where they are really introducing the heating system in the battery in order to do this fast charging. So I don't think that it will be an issue. Again, I should be honest, I am talking conceptually, because we have not integrated at all, and we are far into a battery. But conceptually, you can envision that it will be feasible.
Yeah. Well, another question is, what is the impact of internal resistance of the cell over functionality of cyclodextrin membrane?
Again, automatically here, you need to be careful that you don't want to block your membrane. Okay, because if you block your membrane, there is a current. So again, here we have not built a real practical battery on it. It's still conceptual. And all this question of impedance and so on, they will have, of course, to be handled and to be checked carefully.
And the next question is also maybe very perspective-like. You said it is difficult to go to organic solvents, and how about solid state batteries? Is that even applicable, or what is your perspective view on that?
Okay, again, going to organic, I think it's complex, but there is issues because in this case we can functionalize cyclodextrin to go from a soluble part to insoluble part. Going to solid state batteries, in this case, I need to go to polymer, and this is the big debate of solid state versus polymer.
Yeah.
Now, automatically, here you need to get a safety polymer to do this stuff and to host, I will say, all this biological tooling to do this kind of chemistry. So obviously, it's less attractive, let's be honest.
Yeah, and then we have the question about the mechanical strength and electrolyte uptake of these membranes in the aqueous system. Jenny?
Again, in biology, they can make this membrane relatively easy. But the way that we are doing here to make this all relatively complex, and we use a kind of budget admire deposition. And but this can be made because we can really take what we are doing now, take our kind of classical separator like PVDF, HFP, and so on, in which we are building this kind of tooling inside. And the one why, more or less, for practical cell, I think moving to this kind of solid state membrane will be better.
You have a whole range of questions in the question and answer section, also about how you anchor these alpha CDs to the membrane, and also about the functionalization of the beta CD. And I think you have the chance to look at the questions and maybe answer.
Okay.
So thank you very much
for
an extremely challenging but very inspiring topic. We need now to move on. And next presenter is from Fraunhofer. And unfortunately, Sarah Husman got sick. But luckily, the presentation can be given by Henning Lorman. And it's about specially resolved acoustic, mechanical, and ultrasonic sensing for smart batteries. So welcome, Henning, and thank you for solving and supporting Sarah by giving this presentation.
Hi, good morning. So you should see a full screen, which is a bit mess because of too much information. How can I?
We see it very well.
Let me check how to share the PowerPoint. Now you should see the PowerPoint presentation only. Is it right?
Yes, you can just go ahead.
We see it.
Okay, so hi, and thank you, Christina and Max, for hosting this online conference. First time for me, and such a large audience. I'm quite a little bit nervous, actually. So, originally my colleague Sarah Hartmann planned to give this talk. This talk I'm going to present on her behalf basically goes back to a PhD work of one of our colleagues, Lukas Gold, He's also in the background for the later questions and answer sensors. So the talk will be about, as Christina said, about ultrasonic sensing for state of charge and later also for state of health determination. So the mandatory first slide, why do we need sensor for smart batteries? Quite obviously, we want to increase quality, reliability, and lifetime of the battery. The application we have in focus is electromobility, and here especially the very high requirements for high power charging at the same or even at a higher safety level as we have it today. And if high power charging in a few minutes was not difficult enough, the real trick is to optimize these properties without negative impact on cycle life. You all know it. If you charge your battery very rapidly, the anode potential will drop below the limit where certain effects happen, like lithium plating and so on. And this is what we want to prevent, of course. I always have the image in mind like a surfer who's trying really to surf at the top of a wave without falling down this wave. And with today's accuracy for state of charge estimation, approximately in the lower percent range, it's very difficult to surf on this tip of the wave. And our approach is here to add very cheap sensors that allow us to improve this accuracy of state of charge estimation even further. And an additional factor is that we want to have this sensor that we develop here to be non-invasive and to be really attached on top of the cell, and no sensors like an optical fiber or a reference electrode within the cell. And the technique of choice we use here is the ultrasound time of flight measurement. So, of course, you all know this picture, and you know about the properties of what happens in a battery cell electrochemically wise on the anode and the cathode. And it's also very known that during charging and discharging or lithium intercalation and deintercalation, also the mechanical properties change quite a lot. For the positive electrode here, quite an old-fashioned lithium cobalt oxide electrode, effects are not so massive. The elastic modulus changes only by approximately 30%, where the volume and the porosity are nearly unaltered. On the negative electrode, however, there's a tremendous increase of elastic modulus, nearly threefold compared to the non-intercalated state. And in total, you have a very distinctive change of total porosity on cell level and also on the elastic modulus on cell level. And these changes of properties can be measured, and we try to use these changes to estimate different states of properties of the battery cell. So an ultrasound wave basically consists of two different modes. One is the longitudinal mode or pressure wave, and the other is the transversal mode or the shear wave. The first is kind of like you have an explosion, and the second is back to the image of the surfer, like a sea wave that's traveling over the sea. And the theory we use here for our battery cell is actually quite old. It's from Biot, dates back to the 1950s. And Biot used this theory actually for geological research and for prospecting of oil fields. In his paper, he's speaking of the propagation of elastic waves in a fluid saturated porous solid. And if you think about it, this is exactly what you have in a battery. You have a layered fluid saturated porous medium. This is why we came to the idea that the same theory that was used for oil prospecting can also be used here in this context. And parameters that are relevant for this theory are the elastic modulus, density, and porosity. And you remember, these are exactly the properties that you have changed during charging and discharging of a battery. So how did the original measurement setup look like? It's quite a basic setup. We used very cheap piezo buzzers and glued them on the front and the back side of a commercial 1.2 lithium-ion battery cell, and we operated the buzzers in the oscillation mode in order to trigger longitudinal waves in the cell. What we used is quite basic signal processing methods. We use here a raised cosine pulse with 5 oscillations for the excitation, and we analyzed, in most cases, 2 waveforms, and we used transmission frequencies between 50 kilohertz to 250 kilohertz. And the analysis of the transmitted waves is quite simple. First, you have the time of flight, so the time between exciting the wave and then measuring the 2 wave peaks, and the other is, of course, the amplitude of the measured waves. In reality, we use far more complex procedures to analyze these waves. For instance, cross correlation of the wave, where you basically shift the excited and the transmitted wave on top of each other and integrate over the product of both waves. And the nice thing about these advanced measurements is that they are independent of the actual time of excitation and measurement, but only depend on the time delay between both signals. And for automated analysis of this data, these signal processing techniques are far more beneficial. So for a test, we used the battery cell I mentioned before, graphite versus lithium cobalt oxide, 1.2 amp hours, and we cycle it quite standard procedures, CCCV between 0.1 C to 1 C to a charging end voltage of 4.2 volt, and for the discharging, just the usual controlled current to a cutoff voltage of 3.0 volts. Between 2 cycles, we had a rest step of 30 minutes. In parallel, we measured the transmission spectra every 0.5% of a state of charge, and for a frequency range of 50 to 150 kilohertz with every 5 kilohertz. And if you do the math, this is quite a large number, 8,000 independent measurements per cycle, 16 per full cycle, which are then combined and used for automated data analysis. One example is shown here in this graph, where the time of flight for the 2 wave packages, 1 and 2, are plotted over the capacity of the cell. And what you actually see is where the wave package 1 in the lower half of the graph is nearly unaltered. You only have a time change of time of flight change of approximately 6%. Wave package 2 changes quite substantially, about 20%. A small side remark, of course, all these measurements lie on top of each other for the sake of readability. We shifted them on the y-axis. So what you can also see is, or what we then calculated is that especially wave package 2, the change of the time of flight is in accordance to Biot's theory if you apply the elastic parameters for the charged and discharged state mentioned before. During charging, you have quite a monotone slope and independent of charging rate for all 5 sample years, which is quite useful and easy as input for machine learning in order to estimate cell properties. For the discharging, however, we see two effects. One, we have a hysteresis between charging and discharging, and second, the slope is dependent on the C rate. You see on the 1C discharging has a higher slope than the 0.1 C rate. And the different type of graph, the very same time of flight, this time not over the cell capacity, but over the cell voltage on the left side, and the incremental capacity dq over dV for the electrochemical data. And what you actually see that for the distinctive peaks that are here highlighted by the vertical lines, there's actually a match of the time of flight data with these peaks. And around 4.1 volt, you have quite a substantial hysteresis of the time of flight curve. We think that this is due to a competing effect on the anode and the cathode side. On the very first slides, I mentioned that the cathode does not change so much in its mechanical properties. However, at 4.1 volt, where nearly 0.5 lithium is depleted from the cobalt oxide lattice, there is a change in the crystal lattice along the H1 axis reported, and this has an effect on the mechanical properties, and combined with the strong change of the anode graphite parameters, we assume that this is the effect of this hysteresis we want to further test. Same here for the for the faster charging rates, and here you see three subsequent cycles. And what's interesting that you see here the hysteresis at the low voltages between the subsequent cycles, and that this is correlated to the mechanical disorder of the in the crystal lattice due to the lithium that is intercalated and deintercalated. Okay, my time is up. So conclusion and outlook. What I try to present here is that ultrasound is quite sensitive to the mechanical property changes in a battery cell. It helps us to analyze during cycling phase changes and staging in the graphite anode, plus aging effects like layer growth and pressure buildup due to the SCI. And these signals can actually be correlated to different state of properties of the battery cell. And what we further need, however, is more input of data, for instance, temperature, pressure, electrochemical impedance spectroscopy, acoustic emission spectroscopy, and also our next steps are to actually have an array of sensors, not only a single point of analysis, in order to really localize effects in a battery cell to start creating a smart battery cell. And here I'm very happy to collaborate with partners from CA who make, for instance, these printed sensors, CSEM, who are responsible for the cell and battery management systems, VUB, who are specialists, as we saw in the presentations before, on electrochemical impedance spectroscopy. And hopefully we'll be able to identify more causes of degradation mechanisms that are listed here in the soon future. And I thank the audience very much for the kind attention, and also for our colleagues and project partners that are listed here for their input, and hopefully to be able to have a nice collaboration within the Battery 2030 Plus framework in the future.
Thank you very much, Henning, for this presentation. I think we have time for one question. You have one here about battery electrode changes, packing density recycling. How do you validate the reliability of output waves of the acoustics?
Give a second. Okay. 1 second, please. Please.
If you find that a difficult answer, you can think a little bit and write the answer maybe in the question and answering session later. You have one which is maybe faster. The beauty of Battery 2030 Plus to be chemistry neutral is that you can test new techniques on well-known systems. And Valerio Conta is asking, can you test this also on NMC? And
yes.
Have you tested it, and are there any important differences?
Yes, so it's important to have a change of mechanical properties related to state of charge or aging conditions, and especially high effect you have on the graphite anode, and it's not so dependent on the cathode actually, but we also of course did measurements with NMC, and we see the same behavior as well.
Mm. Yeah, you have actually caused a number of different questions. I hope you have time to read and question and answer, but I'm sorry I have to now. Okay, we will answer. Yeah, and the questions by directly typing in the chat. Yeah, you can do that. Okay, thank you so much, and for taking over from Sarah Hartman, and I hope she gets well really quickly and that it's nothing serious. So I now invite Tane Perecibar from VUB, the University of Brussels, to talk about autonomous polymer-based self-healing components for high-performance lithium-ion batteries. Welcome.
Thank you, Christina. Can you see my presentation?
Yes.
Mm-hmm.
And please show your face so we can see you.
Maitane, you are muted.
Sorry, now I will start again. Okay. Hello everyone. I hope now you can hear me well and you can see my presentation.
Yes.
Thank you, Max. Good morning, everyone. Thank you to the ones staying until the last presentation of this very nice first conference of the Battery 2030 Plus initiative. I would like to first thank the organizers. It's always a challenge to organize a conference, but I think now with these problems that we have in the last time, it's even a bigger challenge. So thank you for that. Let me introduce myself. My name is Maitane Berecibar, and I am the battery team leader at the Free University of Brussels, VUB. And it is my pleasure to introduce Bat4Ever, the project which has been granted recently in the Horizon 2020 program. So as you can see, Bat4Ever in the slide refers to autonomous polymer-based self-healing components for high-performance lithium-ion batteries. To start with, I would like to go a little bit in detail to the understanding of self-healing mechanism itself. The next generation anodes, such as silicon, are abundant and cheap materials that gives outstanding specific capacity. But these materials suffer huge volume changes, like up to 400% during charging and discharging of silicon. So during lithiation and delithiation, these volume changes damage the electrode integrity, causing microcracks or pulverization of electrodes. So as a consequence, electrodes are unable to preserve their capacity in the long-term use because of cracking and pulverization effects. So we can say that the idea behind self-healing is that self-healing coating spontaneously repairs the cracks by pulling back the materials together and offers a unique solution to overcome the negative effects on capacity retention. As you can see in the image below of the same picture, with the help of self-healing coatings, microcrack propagation on the electrode can be suspended. So we can go with this thinking, with this understanding on the development of sustainable, improved, and reliable rechargeable battery cells. It's becoming a must. It's a must already for facing the transition towards clean energy and clean mobility. So in this regard, in order to develop higher energy density battery systems that can be explored with silicon. However, we have, of course, these problematics that I was just mentioning. Focusing on these needs, Bat4Ever would like to, or it's focusing in the next that we will develop. We will develop self-healing functionalities through polymer binder surface coating to protect electrodes, as well as the utilization of silicon anodes. We will understand the oxidation and thermal stable cold-shell structure and MC cathodes, and we will develop, of course, novel electrolytes based on polymer ionic liquids. In this regard, for facing these issues that can be tackled by the use of system-tailored self-healing battery components, Bat4Ever is aiming to achieve or face 6 different objectives. As you can see here in the slide, they are the 5 of them, sorry. The first one will be on the development of innovative nanostructured and self-healing polymer supported by the battery materials. The second objective, very much linked to the first one, is the development of innovative ion gels embedded for self-healing battery components. And the third one, of course, goes to the modeling and characterization. So we will develop advanced techniques for characterization, modeling, and simulation to define all this that we have studied before and to tackle the objective 1 and 2. After this, of course, it's extremely important to develop the cells, to make the prototypes, and to understand the process of assembly with all these new characteristics of self-healing, And the last objective focuses on the validation of everything that has been done before, together with maybe some adaptations, tailoring of this lithium-ion battery properties to go for these high-performance self-healing cells. Not only these very much scientific objectives, but we will also understand economic issues and LCA assessment on the full for the full process, from the full understanding the materials until the second life of recycling state. So let's start a little bit with all the objectives one by one. Here we can see objective 1 and 2. Objective 1 refers to the development of innovative nanostructured and self-healing polymer supported by battery materials, in which for this purpose, But Forever will focus on the silicon anodes with self-healing polymer binder, which will be synthesized. In addition, the oxidation-resistant thermal stable nanopatterned NMC core shell structures will be synthesized, and as well, novel, of course, polymerized ionic liquids will be developed. Together with this, I put it both together. Objective 2 mainly focuses on gaining self-healing properties of all these battery components, and more in detail, we will develop the synthesis of ion conductive and mechanical flexible ionoyels to, of course, compensate this big issue on the volume changes and interfacial stress. But Forever will as well understand and study the surface functionalization of anode and cathode particles by appropriate functional groups. We will understand the incorporation of the novel electrode concepts into cathodes. And within this objective, we will as well develop the synthesis of electrochemically stable ionic polymer electrolyte membranes. I would like to go a little bit more in detail on the characterization and modeling, because it's part of the work that we will develop at VUB. So this objective focuses on developing advanced characterization tools for battery and modeling and simulation techniques to define the battery component properties under the, of course, introduced self-healing influences characteristics. And for this, comprehensive interpretation of the results obtained within the framework of But Forever will be studied, such as the advanced materials characterization with ex situ correlative microscopy, in situ, and in operando approaches. For these different models will be developed, as you can see in the slide. We will focus on ab initio investigation of thermodynamic stability. We will understand, or we will develop kinetic Monte Carlo studies, modeling and simulation up to the cell level, and of course a macro scale multiphysics model. Within the in situ and in operando techniques, we will provide, we will need and we will provide a deeper knowledge of microstructural changes and self-healing during operation. And of course, thanks to these techniques, it's very important because we can, it's possible to visualize the microstructural changes, the volume expansions during cycling that the materials that we are using will perform and will create. So these techniques will allow us to see the effect on self-healing mechanisms during the operation. And in addition, in the But Forever project will develop components with these self-healing attributes, which will be very novel. So of course, in order to develop an understanding on the potential usage and atomistic approach like Pinish investigation will be used to identify the stability of electrodes and all components under the operation conditions in a thermodynamical manner. In a next step, for larger scale modeling, kinetic Monte Carlo modeling and simulation from self-healing material to the cell will provide knowledge for the interfaces. And of course, microscale multiphysics models developed on the novel self-healing battery components and development for the self-healing lithium-ion batteries will give very valuable insights on time saving in know-how of the cell development and the performance evaluation. We have already seen objectives related to the self-healing materials itself. We have seen how we will tackle characterization and modeling, but of course we will also understand cell production and assembly. So for this, our aim is to develop innovative self-healing and cost-effective battery cell or prototypes. Let's see how far can we go to, and understand the assembly of these cells. So for this, we will understand the prototype manufacturing and self-healing integration to the desired cell designs. We will see battery fabrication and process parameter optimization, and of course the manufacturing in this understanding of cost-effective, safer, and higher performance on the battery cells. For this, we will of course use already developed work for assembly of novel cells. However, with our new characteristics of self-healing, we will need to benchmark, we will need to understand, we will need to adapt our appropriate battery assembly methods, and not only the assembly, but also the design will be the adequate one for developing our prototypes at up to 2 ampere-hour nominal capacity. On top of this, an extensive parameter optimization will be developed and verification of the battery fabrication process itself that is going to be done within the project. So not only the assembly, but we will need to validate as well all the chain that we have been that we will be working on it. So for this, we want to validate and adapt, of course, when needed, the properties of these new novel self-healing batteries. And for this, we will validate it in a real life scenario. And we will, not only that, we will have an environmental and economic analysis in which we will include second life and recyclability evaluation. For this, at VUB, we will do this environmental and economic analysis. So several steps will be studied. Of course, these new self-healing cells with supplementary materials may have higher environmental impacts and costs. However, the increased performance may balance these supplementary impacts and costs. So the objective is really to go deep and to evaluate these trade-offs, not only for the impact on climate change, but also to understand other kind of impacts such as acidification, toxicity, and particulate matter formation, for example. So the increased lifetime and performances may ease sometimes to second life applications, which can be studied in different ways. There can be a possibility to reuse the same purpose, or it can go to a second life scenario such as stationary usage. For this, here we have an example in which VUB will investigate the sustainability criteria, so for environmental as well as cost aspects of these new self-healing functionalities from, of course, a full cycle life perspective, starting from the raw materials, manufacturing, until the end of life. So this example that we can see in the slide shows benchmark battery and its impact on climate change, considering the different subcomponents of the full battery. So at VUB, we have dedicated databases and software to develop this that we will use, of course, in the framework of the project. As I could not really give a lot of information on the project because it's going to start, so unfortunately we don't have results, but I wanted to give an overview as promised in the abstract. I wanted to give some insights related to these self-healing new materials that we are going to use. So this is a recent scientific outcome from VUB. So while the Bat Forever project will study the effect of self-healing functionalities on the performance of silicon lithium-ion cells, VUB has recently shown that pressure is a key parameter that defines the performance of silicon-based cells. So we have developed a cost-efficient measurement setup to understand this pressure, to optimize the cell performance, while also enabling inoperando measurements during battery recycling. As you can see in the right side, extensive investigation showed that the capacity, rate, capability, and lifetime of the silicon-based significantly is affected. As an example, and going a little bit more in detail on this, the characteristics.
I have to ask you to wrap up now.
Yes, 1 minute and I will wrap up. So I shown in the figure in the right side in blue that the cycling over the entire lifetime, and in red we can see the degradation. So it's seen that the pressure can also be related very much to battery states as a state of charge and the state of health, which will be very, very valuable within the project and on other kind of activities. To finalize, I want to just make some impact on the project itself. We are aiming at Bat Forever to, of course, increase the performance on batteries by increase the lifetime, increase the capacity retention, of course, use a wider operation temperature window, also making available fast charging, and of course everything in a cost-effective system. In this regard, cross-linking activities, I think we are facing very well, that are already very well explained in the roadmap. So we are focusing at different levels, at material level, at manufacturing, modeling, and of course application level. So I would like to thank the Bat Forever team, and of course my colleagues at VUB that helped me to give you this insight. Thank you very much.
Thank you. We have not really time for any question, but I will pose one question anyway. And there are several questions from several people, so I will summarize them in one question. And that is very much the self-healing part. Is that the polymer binder and to really handle the silicon anode and the cracks in the silicon anode or so, or is it something different? And is the polymer something different from CMC and other classical binders?
Okay, that's a very nice and interesting question. It's related to polymer binder, and we will see how we will tackle within the project and have the best performance of it.
Okay, thank you. You can also go into the question and answer, and if you want to answer more in detail, the questions directed to you.
Thank you, Christina.
This was our final presentation for this meeting, and you can see here on the screen all the presenters of today, and I'm extremely grateful for all of you, and thank you all for your contributions and for keeping the time so we can actually end our meeting. I'm also very happy for you who have signed up and attended this meeting. Some of you coming all the way from Australia and from Asia and Africa and all over the world, despite the differences in time. That's really impressive. And I hope you actually will respond to our survey. You see it on the screen, so that we can know what you thought about the quality and also about what we could actually offer you in the future. When we started this conference, Max Millian-Fischner said that we had more abstracts than we could accommodate in this conference. We plan to sort of try to accommodate them in a later stage. And I think that is really, really important. You have also been asked the survey earlier, where you were asked if you were interested in our newsletter. And of course, you will have the chance to go into the web page of Battery 2030 Plus and sign up for more. And I think I also need to very much thank Christian Punkt. Without your punctuality, I don't think we could have managed, and your way of practicing with us before and between the different sessions has been absolutely fantastic. You haven't seen, the conference attendees have not seen all the work that is behind also so something that looks like a simple web conference is not as simple as you think. So thank you so much, Christian. And for the whole team at KIT and Helmholtz Institute for
Yeah, thanks, Christina. Of course, I haven't pulled this off alone. There have been people such as Maria, who was in charge of the polling, Daniel Messling, he set up the registration website. So thanks to my team also for offering themselves as guinea pigs when we tried out all this conference things. So it was a great conference. Thanks, Christina.
Yeah, thank you. And thank you for the scientific organizing committee also. Not everyone has shown their face today in the conference, but you have definitely also selected among the abstract to make a good presentation. And this is actually the big finale of the preparatory part of Battery 2030 Plus that will end now the 31st of May. And but we will not disappear. We will show our face in many different occasions, hopefully in the Web European Sustainability Week in the end of June, and in also other kinds of web meetings and seminars, etc. And then we will fly off officially again 1st of September, and we will welcome you back to many different meetings and occasions. I hope you will like to join us. So thank you. Is there anything else you want to add, Max?
Yeah, actually not. You have said everything. I'm looking forward to a follow-up meeting if this shall come. I enjoyed it very much, and I also saw that there has been a vivid discussion on the questions and answers section. So people started to interact with each other and use this also as a tool. And I think this is an aspect which we don't have in regular conferences. There you could do it at a coffee break or so, but here it's really done online. I miss you guys to see you personally, but from my opinion, it has not been so bad. Yeah, so and I'm really looking forward to our next meeting.
Yeah, look forward to see you personally and on the web also in the future. So thank you very much. I by this close this conference and wish you best of luck in the sunshine. At least we have sunshine where I am, which is not so common, but today is a good day. So thank you. Bye-bye.
Thank you, Christina. Just for the attendees, of course, we have a video recording of this conference. We'll process the video in the upcoming 1 or 2 days, and you will all receive a follow-up email of this event where you will get access to the video recording of yesterday's and today's session. Thank you.
Bye.